welcome to engineering applications of first order differential equations. Observing the law for conservation of mass, we have the volume of water leaving the tank is equal to the volume of water supplied by the tank. If this isn't happening, you've got a bit of a problem. Therefore, we can write that the volume of water leaving the tank is equal to this function here, and A is the cross-sectional area of the exit pipe given by that function down the bottom there. The exit velocity of the water can be derived from Bernoulli's equation. Using some assumptions for some of the larger tanks in civil engineering applications, we can get this equation here. It follows that the volume of water leaving the tank is equal to this function here, equation 2. If we let HT equal the drop of water level over time, we can write that the volume of water supplied by the tank is equal to this function here. Note that it's negative as this quantity is lost from the tank. It follows, or we can now formulate the following equation by equating the volume leaving the tank equal to the volume supplied by the tank. Rearranging, we end up with this difference form here, and then simplifying again, we end up with the variable separable differential equation below.
Up here is the equation that we start with. So to get to the next equation, all we do is we take this root ht to the other side, swap it with the delta t, and we produce this equation here. Once we have this equation, we just simply integrate both sides. We rearrange this section here to put our minus ht to the minus a half, and this section, these are the constants here. So we just take them up front of the integral, producing this section here. From the ht to the minus a half, we get 2 root h. Then from these constants just simply multiply by the integral of dt, which is just t, plus the constant c.
As what Kieran prepared earlier, we now test the initial conditions. As this is a real-world solution, it's going to have it has a physical condition. So at h naught equals h0. So plugging this into our equation, we get this, and t, as we remember, goes to 0. So therefore, we get a constant of 2 times the square root of h0. Now, putting this back into our original equation, we get this. From here, you can further simplify it by dividing through by 2, and then removing the square root signs by squaring the right-hand side.
From the variable separable equation, we can get the height of the water at any given time. We then plug this into this equation, and this gives us our exiting volume of water at any given time. It comes in handy in real-world engineering applications such as hydrostatic schemes, also water distribution from dams, and also things around the house like hot water tanks. Alright, we've got a quick video prepared just to show you a real-world application, or not quite real-world application, but amusing application of what we've been going through.
If you think it's safe to drink from a fire hose, why not, Dad? It's just water. All right, well, turn it on. I'm very thirsty. Nice job, Chris. You got my shirt wet.
Good.